This is the second most expensive and most over-engineered moka pot in the world. Creating it took hundreds of hours of work and over $250,000 worth of equipment. But why would anyone go through all that to replace a readily available product? And will this even be any better? Also, what's the most expensive one if it's not this? All these questions will be answered. So let me tell you how we got here. To outside, the Alpha Lasers headquarters, without whom this project would have been impossible, and who are also the sponsor of this video. This is a moka pot. It works by using an external heat source, like a stove, to boil water inside of the boiling pot. This creates an internal pressure that pushes the hot water through the coffee powder, thereby brewing a coffee. Since it doesn't have any heating elements or pumps, like other coffee makers, it takes up close to no space in your kitchen. And that makes it the perfect way of brewing a coffee when camping or hiking. Which brings us to our biggest problem. If you want the coffee now, you have to wait at least 4 minutes before you can have some. That's unacceptable. So, let me tell you how we're gonna fix this. To make coffee faster, we need to increase the surface area of the boiling pot, thereby increasing the total amount of heat that can be transferred to the water from the fire, and by extension make it boil faster. If you take that idea and spend way too much time and money developing a product around it, you end up with something like this. This is a moka pot where the surface area has been increased as much as possible. The entire body acts as a car radiator, except in reverse, meaning it takes heat from the environment, in this case a gas flame, and transmits it to the water that needs to be boiled to be able to make coffee. And because of the larger surface area, it boils the water a lot faster than the traditional moka pot. And there we go, job done, easy peasy. Don't forget to like, comment and subscribe and click on the bell notification. No, wait, stop. Remember when I said that's only the second most expensive and over-engineered moka pot in the world? Yeah, come on. Have a look at this. The gas burner is glowing red hot. That is wasted energy, meaning there's still performance left on the table. If only someone would spend even more time and effort developing a gas burner that is integrated into the radiator-style moka pot that is subsequently water-cooled by the same water that is used to make coffee, making the entire process mega efficient and fast. Me? Well, yeah, I guess I don't have anything better planned for the next few months of my life. Alright, let's go, come on. So, if we want to go ahead and make this a reality, we will need two things. First of all, we'll have to design both the gas burner and the moka pot from scratch, as well as figuring out how to combine them in the most efficient way. And second of all, we need a metal 3D printer. Luckily, just when I was starting this project, Alpha Laser reached out asking if I would like to collaborate with them in some way or another. Which was great, because they make metal 3D printers. So, the only thing left to do is to design the most over-engineered moka pot in the world. Normally, when you're designing something with the help of 3D printing, you just create a quick design, print it, and modify the failed features. Then you repeat the process 10 to 20 times. And while we could technically use the same development process with metal 3D prints, the cost of metal printing is quite a bit higher, making this approach unreasonable at best. So, during the development, we're just going to be using plastic. This has two great advantages. First off, nobody's gonna go bankrupt in the development stage. And second of all, which is really cool, we can easily benchmark which design element works better than the other by simply looking at how long the part lasts before it melts or goes up in flames. It also makes pretty good YouTube content, I have to say. So, let's break this down. Essentially, we're trying to heat the water. If we make a geometry that provokes circulation of the water inside of the boiler and brings cold water to the hottest parts of the print, then the plastic print will survive for longer because the cooling is better. Better cooling means more heat transfer, means faster heating of the water, which means faster coffee. So, the longer the plastic print survives in testing, the better it will work once it's printed in metal. But before we get to the point where we can test an entire integrated system, we have to develop a lot of subcomponents from scratch. First, we have to look at the nozzle. After testing many different sizes, I figured out that the 0.4mm orifice is the perfect size. Which of course raised the question, would a normal FDM nozzle work as well? And yes, it does. Not only well, it works better because the results are a lot more consistent than with the 3D printed one. However, notice that all the flames are yellow. This means that the flame does not have enough oxygen, and it cannot achieve an optimal combustion, making the gas burn a lot cooler than what it actually could. To get the nice hot blue flame that we want, I developed an air mixer that mixes the gas with the air. This took many revisions, where a lot of variables were tested. And in the end, not only did I figure out how to make a blue flame, but I also figured out how to make the flame stick to a surface, which will be very handy when it comes to heating up another surface. In our case, the Moka pot. The next technical challenge was of course the gas distribution system, which is responsible for even heating of the entire surface. In this shot, you can clearly see how the pressure gradient inside the gas distribution system affects the flame height. Ideally, we would want this to be completely flat. And together with that goes of course the cooling of the gas distribution system. My initial idea was to create a thermosiphon. A thermosiphon is a system where the difference in density of the hot and cold water creates a natural pump that circulates the water. While in theory it's really cool, in practice the flow is too slow. And on this scale, the heat dissipation is simply not good enough. After many tests that I tested both the gas distribution system as well as the cooling, I figured out that the best way of cooling a system like this is by using a steep surface and utilizing natural convection to remove the hot water from the burner nozzle. To wrap up the design phase, we need to take all these learnings and put it into one single design. But that is easier said than done. Not only do we have to put all of these things into a single part that is printable, but we also have to maintain compatibility with an existing Creality pots, which is not only achieved through the threaded connection, but also the total size of the vessel. This needs to have the same volume of water relative to the water level inside the pot. Otherwise, you would get too much or too little coffee. After a few weeks, I ended up with this design. The top part is very similar to the first design, where you have the radiator slots for improved heat exchange. But on the bottom, you have a burner that is cooled by the same water that is later used for the coffee. The top and bottom part are connected with these support structures that are hollow and allow for even more water to be transferred between them. They even add more surface area for the flame to heat. So, the only thing left to do is to print it. Now, for some reason, Alpha Laser didn't just want to send me one of their quite valuable print and prep stations. The blender. Oh. No! Not sure why. So, I did the next best thing. After a quick coffee and introduction to the team behind the 3D printer, I got to see the first print finish. And apparently this was the longest print they had ever done at the company, which by extension makes it the most expensive one. For now. Because right after the print finished, I got to slice, prepare and start the next print myself, which was going to be the new longest print at the company yet. The printer works with the same principles as the laser powder diffusion metal 3D printers that I used in one of my previous videos. In short, a laser melts metal powder, making it solid, and then repeats the process layer by layer until you have a 3D object. However, unlike that previous printer, this one does not use built-in print and powder chambers. Instead, it uses these cartridges that contain the metal powder, and they come in different sizes. There's one for the powder supply, one where the part is printed, and one for the overflow. The reason I'm telling you this is because the design I made is so big that it would only fit in their biggest print cartridge. Of which, at the time, they only had one available for testing. This means we would have to use a smaller cartridge for the powder supply, which again means that we would have to refuel the printer 2 to 3 times during this 3-day print. In itself, this is not an issue, since changing the cartridges takes less than a minute. But in my infinite wisdom, I proposed that we should try to run the machine a bit extra lean overnight, to time the refill perfectly with the start of the next workday, and thereby avoiding it stopping in the middle of the night, waiting to be refilled. This was a mistake. Let me explain why. Usually, the recoater pulls more powder over the print surface than it needs. This is because the powder shrinks when it's melted and solidified. When running the machine lean, we reduce the amount of excess powder, thereby making the powder supply last for more layers. But thereby we're also running the risk of running out of powder in the middle of a layer. This is very bad, because if there's no metal powder there to melt, then there will be no metal there after the fact. Which, of course, is exactly what happened to us. Luckily, the mistake was noticed, and the print was saved by simply increasing the excess powder amount back to the recommended levels. But we already knew that the print was going to leak right out of the printer. And as if that wasn't enough, in the whole, testing and design phase, I completely forgot to add my and Alpha Laser's logo to the first design. But luckily, we were at the right place to make mistakes like this. You see, Alpha Laser doesn't only make metal 3D printers. This is a tank tread mounted high-power laser beam welder that can weld virtually any metal with unrivaled precision thanks to surface scanners and multi-axis computer controls. If you can't bring the part to it, this thing will come to you. But yeah, the Moka pot was quite easy to just bring over to the already set up and ready to go stationary laser welder, which they also make. So we just used that one instead. And after a few practice runs, I, with a lot of help from the others, got to weld a set of 3D printed bronze logos onto the stainless steel Moka pot. Gotta say, not bad for my first ever laser weld. A quick sandblasting removed most of the apprentice marks and made me the welder I ain't. Once the second print finished, the one with the holes that we know was gonna leak, we took it right over to the welder to patch up the holes that we could see. So, after way too many engineering hours, 4 16-hour workdays at Alpha Laser, and who knows how much money in materials, we can confidently say that these two Moka pots are the most over-engineered and certainly the most expensive ones in existence. But are they any faster than the off-the-shelf Moka pots? Let's find out. Before we test the big and expensive one, let's start off with this simpler design that is more comparable to a standard Moka pot. We set up a test with the same burner and the same amount of water to see which pot could boil the water the quickest. The 3D printed pot used just above 50 seconds to finish the race, which is very impressive since the traditional pot used almost twice as long, with almost 1 minute 40. Remember, these are the same conditions. That means if I now save 1 minute of my morning routine every morning, then it will only take me 69 years to break even with the time investment I put into this project. Nice! Anyway, coffee's done. So here we are, trying the first brew with some of the team members at Alpha Laser. It might have been a mistake to buy the absolutely cheapest type of coffee we could find for the first test. But the pot is undoubtedly a functional and record-breaking Moka pot. So, what about the big one, the one with the integrated burner? Well, turns out if you can't see the holes, then you can't really weld them shut either. And sadly, while the pot looked awesome, it's impossible to build pressure in a coffee pot that has a leak. But we did try the burner with some water in it, and it got the water to boil very efficiently, with what can only be described as very low amounts of gas flow. I can only assume if I were just a little bit more patient, then now I would have 2 fully functional, record-breaking Moka pots. Overall, I'm very happy how these designs turned out, and they will undoubtedly be used in upcoming camping trips and hikes, where they certainly will make everyone in the campsite incredibly jealous. Thank you all for watching, thank you Alpha Laser for sponsoring the video, and a huge thanks to the AL3D team, who supported me so much in this project, both with the filming and the pre-production of it. Thank you all for watching, see you guys next time. Bye!